might have, what I've used this for actually is where I feel like sometimes I'm not in sync with someone. And you know, like you probably have you're around a lot of people here, and sometimes you feel like you're talking about something or they're talking about something and that person doesn't get you. It will be reflected in their language. But it'll be interesting to pull it and see how much of a match it is. And then look at their text too. You can pull and do an ocean analysis, and it might be something that's very different than your own personality, which might be causing it. It will help you with interpersonal interactions. So how do you do this? We're going to use something called cosine similarity. And in this, I'm going to show you what a vector is. And analysis. Who had vectors? Elias, you had it? Okay. So you're going to tell me like if this is different. I don't like physics. That's recorded, but I don't like physics. So I'm happy to not do it. So let's say, all right, listen up. Let's say I have a toy sentence like this. I call these toy sentences because nobody says this. But a quick brown fox jumps over the lazy dog. And by the way, generative AI, it's built off of these ideas. So it's not like generative. You're actually seeing a little bit under the hood of generative AI. So S2, I'm going to say something pretty close to it. I'm going to say a fast brown fox leaped over the sleepy dog. Like this. These two sentences, from my eyeballs, you can see that it's similar. So I'm going to show you this as a toy example of how we build this out into being vectors. So the first thing we do is we take the notation we use is this little arrow. And I'm going to make a vectorization of this. A vector is just a shish kebab of stuff that represents this original string. So these words, like those are not important, like quick brown fox, that's important. The words that are not important, we call them stop words when we program. We want to take those out. I'm going to take those out and put everything that seems relevant inside one list. So S1 turned out to be brown dog. Oh, let me see, I'll erase this. Hang on one second. Quick brown fox. Oh, that's how we denote a vector. So all of this is notation: jump, lazy, and dog. That's how we just make the list. It's like it just represents the list, and it's so that you don't have you've already used the ordered pair for the Cartesian plane. So it's a mathematician coming up with a new way to represent this list. That's all you're doing. And for S2, the list is going to be fast, brown, fox, leaped, sleepy, dog. I better see some note taking here because there's a lot of math that's underlying this, and you'll need it.
Does this sound like those players checkers were?
They absolutely are. Very nice. Okay, so now the next thing you're going to do is you're going to actually look how frequent something shows up in the first vector and the second vector. So for example, in the first vector, it's not well written out in my notes, sloppy. The number of times certain, let me do another thing here so I can see. I'm going to put together a list of words. So here I'm going to put a big fat vector, which has all the words compiled. And that's a script DV. So I just took all the words that were being used and I put them, we call that a corpus. I don't know why that's what it's called. Sounds kind of like a corpse, but it's not. It's like you take all the words. So on a large scale, when you're doing checking for plagiarism, you would take all the possible words inside one huge paper. So this thing could be huge. That's why we call this a toy example. It's not the whole thing. And then you're going to go back and make a vector of how frequent each word showed up in each one of these sentences. So I'm now going to make it, turn it into numbers. So I'm going to have you take boards in a second to do S2, but I'm going to do S1. So S1's frequency vector is going to just look at how frequently, I'm put a 1 here. The first one used the word brown. How many times in this first sentence did the word brown show up? 1. How many times did dog show up in the first sentence? 1. How many times did fox show up? How many times did jump show up? Jumps. I should put jumps here. 1. How many times did leaped or let leap show up? 0. Sleepy showed up in the first sentence. 0. And the last one was dog. Did I do dog twice? No. Sorry, I lost track. So here, brown showed up once, dog showed up once, fast showed up, none. Fox showed up once. You get it? Jump showed up in the first. Jump or jumps is considered the same. We call that stemming. If you're going to CS, this is called stemming. We're stemming the words. So jump showed up once, and then lazy showed up once, and leap didn't show up at all. Quick showed up once. Sleepy did not show up at all. And I think I'm done with my V. All right, I would like you to make the frequency vector for the second sentence on the board. Yes. You're better at keeping track of things. So brown showed up once. Dog showed up once. Fast showed up once. Fox showed up once. Jump did not show up. Lazy did not show up. Leap showed up once. It's a stemmed word. Quick didn't show up. And sleepy, right.
And that means it's like.
It's the same word. So you don't want jumps,
Like
jump
fast
like.
and quick.
Yeah, leaped and jumped. Yeah. Leaped is different than jump. That's a different word.
Okay.
Leaped and leapt and all words associated to leap are called the stemmed version. So I accidentally didn't even think about it. It's such a habit now. They're considered the same. So leap, leaped, and leaps and leapt are all considered the same, right? You would say think of that being kind of the same word, right?
It's like fast and quick.
Fast and quick are two different words.
Okay, so it's the actual word.
Quick and quicker would be the same because it's quick and quicker came from the same root. Do you remember in the spelling bees where they go, what's the root of that word? Like it's the same root.
Okay, so it's only the word itself,
not the meaning. Chris, make sure you have good notation. You have these like V brackets on them. Like they have to have that. Can't have the round brackets already been taken by Cartesian plane. That's math. It's full of notations. All right, you should have the same thing as me. Should look like this. All right? If you don't understand, make sure you understand from your partners. Lucas, make sense? Okay, once you have that, take seats. I'm going to do one calculation. You're going to do, great, we have S1 and S2. So I can do one and you can do one. Vectors are not numbers. They're a shish kebab of numbers. That's what they are. So you can't do certain things with vectors that you could do with numbers. But one thing you can do is talk about the size of that vector. We use something called magnitude. And it comes from Pythagorean's theorem, but it has something to do with magnitude. So I can tell you what the size of this vector is. And how I calculate the size. That's what you do. So on the first vector, if I go back, I could give you a formula. I'm not giving you a formula for a reason. I'll give you all the formulas when we get there. But this is what you do. You take each term and square it, and then square root the sum. So let's go back to that first one. I'm going to do S1, and you're going to do S2. So the frequency vectors. So over here, I finally learned how to do this. Why is it not doing this? Okay, it says copy was successful. So there's my vector. Here's how I calculate it. The first term is 1. So I'm going to take that first term and square it. That's that guy, plus this guy squared, plus this guy squared, which gives me nothing. I'm writing it all out so you can see what it is. Formulas are just numbers with x's replaced for the numbers, not the other way around. Like you want a good example in your head. And if you look at that and sum it up, I really have 6 of these. Square root of 6. Yes. It's a real number. I can tell you now, I can compare one vector to another by size. So you find now the magnitude. Go back to your boards and find the magnitude of S2. Is that the sign for yes, it's like an absolute value, but you have two. Kind of like you're finding the absolute value of that. Didn't want ones and zeros. You wanted like really bad numbers. Yeah, that it's like an absolute value, but it's a double. It's like yeah. That means the size of the magnitude of SF2. And don't forget to put equals. It's like absolute value equals. It's kind of like the absolute value. This is indeed, yeah, she should have got it squared to 6 again. Oh. All right, take seats. Next up. I'm going to show you the concept of why all this is true. There's geometry behind it. We're getting there. The next step is something called an inner product. Students confuse this with multiplication. When you multiply two numbers, you always get a number. When you dot product two vectors, two strings, two shish kebabs, and you dot product them, you get a real number. So it's not the same as multiplication. This is what we call not closed. So when someone starts using the dot product as a multiplication, I know they didn't get me. It's like a sign. But this is the symbol we use. I put a little f up there for frequency, dot V2F. The way you do it is you take product. The way you do it is you take the first two components and multiply them and add. Let me put both vectors up here. You ready to do all this on your own without me lecturing about it all? All right, because I'm hearing a lot of buzz out there.
Like a bunch of civilians, there's like people out there. We're like a zoo. Yeah, there's like people like wait, what? Oh, yeah. It's a pyramid.
Gonna ask them if they wanted to come here and find out if they need to break up with their spouse. All right, so the way it works, dot product super easy. Even my worst student, this is being recorded at Montclair State, would pass the class. They would know how to do the dot product. So everybody in here will know how to do the dot product. All you do is you take the first element here and multiply it to the first element here. And then do the same thing with the second element here, which is this guy here. I'm doing the write out for you if you don't know what it is. So this is the dots up there, and this I think there's no way to do it. You could do it as a formula, and I can do that for you. But so I take the second elements, I get 1 times 1 again. But the third one, I get a 0 times 1. And the fourth one, I get a 1 times a 1 again, plus dot, dot. I'm just going to do dot, 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 because I'm going to lose track. But I get 3 when I finish this out. I'm going to get a bunch of zeros, so middle terms will drop out. So for example, do I get 3? 1, yeah. 1 times 1, 1 times 1, 0. Yeah, and then the rest, I'm going to have a bunch of zeros. So every other one is going to drop out. So I'm going to get 3 of them left. Does everybody understand what I did? You're going to have lots of dot products to take.
Can you compare 3 different things?
Yes, you can. So you can say if 3 people don't think, yeah. In fact, I use this all the time because sometimes when you must think I'm the devil. I use this to understand when I'm talking in front of a group why the 2 people fit together or 3 people fit together. They might not have the same motivation underlying it, but their language syncs for a particular reason. For example, if one person has the language of superiority and this other person is a subordinate, they sync well together because the first person's talking as if they command and the second person's responding to that. So they actually do mirror each other's speech. So if you're talking to both of them, you kind of have to take that into account. Anyways, you get 3 when you do this. And then I find something called cosine similarity. And this is the frequency vectors I'm using. This angle, this theta, is the angle between these 2 vectors if you plotted them. You can't see these vectors if you plot them because they have more than 3 dimensions. If there's 3 dimensions, you could draw it out in space. But they have.
Do you multiply the 6 in the bottom?
Yes. So you have a square root of 6, square root of 6. So on the top you have a 3. On the bottom you have a square root of 6 times square root of 6. So it's 3 over 6, which is 1/2. This number tells you how similar the 2 sentences were. Right now, it's 0.5. The closer it is to 1, the closer those 2 vectors are to each other, and the closer the sentences are to each other. If they're the exact same sentences, then everything with the numerator and the denominator would be 1. They'd be the same. Make sense?
Oh, what's the bottom of the equation?
It's the version of the magnitude of the first vector, magnitude of the second vector. So we already calculated that. You did one on the board. We use double hash marks or double lines to represent magnitude. So these 2 sentences are pretty similar. I'm going to give you 2 sentences. I'm going to have you try it from beginning to end. All right? Give it a shot. Try this one. Beginning to end. Find the cosine similarity of these 2 vectors. S1, the first sentence is the quick brown fox jumps over the lazy dog.
Are we able to use words?
Yes, you'll want to. And the second one is mathematicians. This one's easy to compute, actually. Prove theorems using logical reasoning, what do you think you should get?
0.
Do the math. So you're first going to make a corpus of all the actual words that are not the, right? You're going to make a big list. These two sentences have nothing in common. So one of your frequency things are going to come out, one with lots of zeros, and the other one's going to come out zeros with lots of ones. See what happens. Do the math and show it. I can do the V for you, the big V. I stemmed them again by not even thinking about it. Yes. And then make your frequency back. So you're going to have 1, 1, 0, 0, 0. Second one has 0, 0, 0, 0, 0.
Does it matter the order that you put the big V, all the words? Does it matter exactly the order? I mean,
It's going to make your math easier for this one. Yeah. Oh, yeah. No, like the first sentence, the first stuff and the second stuff, the order of the first stuff doesn't matter. You'll see why. You realize, sure the magnitude is 0?